Welcome to third lecture in data mining then. And the third lecture is, at least we are planning it a little bit more interactive. So the idea was for you to watch some videos about SVMs so that now we can start discussing that. Have you watched those?
Yes.
Okay, we have one yes.
Yeah, I watched the first one.
Yeah, me too.
1.5. Me too was the first one or both?
Yeah, first one.
Okay, 2 out of 3, not bad. Okay, so what did you think about those?
For me, from Henrik here, I would like to have some kind of background. If you could describe why these vector support machines are so important and how to use them. Of course, he described that in the lecture, but we jumped into a course where they have several lectures before, I think.
Yes, but well, we have also had several lectures before. They of course
yeah.
more.
But at least for me, maybe I didn't understand everything you described in the previous lectures. But could you please give some kind of a little bit overview or introduction to this?
Mm-hmm. So if we start thinking about what kind of problem SVM is trying to solve. How would you describe the goal of SVMs?
To classify a data set.
Mm-hmm. So if you compare SVMs to, for example, decision trees, as we have talked about decision trees on the previous lecture, is it the same problem? Is it solving different problem?
Yeah. It seems to me that the SVMs, there you had some kind of workflow to make this more automatic than the decision trees. Is that correct? Like to be able to program that for a computer to do.
So if you go into details of how this is actually implemented, then in a sense you are right. It consists of more different steps than a decision tree. But if you think about what this is used for, so assuming that somebody has already done the work, so there is either a library or a program with graphical user interface or service on the web, however you want to organize it, which implements all of this thing. So from the perspective of the user, it doesn't really make big difference, right? The goal, you still want to solve exactly the same challenge. You have some data. Let's talk for simplicity about a binary case where the decision is yes or no. So you want to separate, be it patients into those who should be discharged and those who should be kept in the hospital, or be it some kind of machines into those that will fail and those which will not fail anytime soon, and so on. The way of making this separation is different. It's quite a bit more complicated than a decision tree, but it's important to understand that the goal. Hello, Malu, can you hear us? We cannot really hear.
Yeah, Henrik can hear you, but maybe something has to be muted here. Is it better now, Slavomir?
No, I think it's fine. Yeah, so it's So if we keep going, so the goal of SVMs is the same as with decision trees. You want to be making decisions, right? So you want to, based on some historical data where you have some examples of those decisions, you want to build a model, and then you can use this model in order to make decisions about new data where you don't know what the decision should be. Everybody agrees with that?
Yeah. Yes.
Yeah. Yeah.
Yes.
One thing also that I stumbled on is that the mathematics knowledge I have from from the university is not very up to date. And for example, the Lagrange multipliers, I'm not. I don't remember fully. Can you say something about how the Lagrange multipliers came into these equations?
So we can go back to that later. I think it's important to understand that, of course, if you would want to follow every single step of the lecture, you need to kind of freshen up on this kind of knowledge. At the same time, it's not really necessary, right? It's
no. Okay.
If you know that the whole point of this exercise is to solve the optimization problem, to actually find the minimum of this function. Of course, it would be nice to really understand how this is done in an efficient way, but to be honest, there is, well, too much knowledge. We cannot know everything, right? So if you don't understand the exact details of how this is done, that doesn't really matter, because as the professor said, there are libraries that will do it for you. So if you just want to use those techniques, you don't need to understand every single step. And if you have a rough idea of what Lagrange is, that's perfectly enough. And to be honest, many people who use SVMs have no idea that something like Lagrange exists, and that's also fine, because again, there will be library that solves this optimization problem for them. We can go a little bit into those things as we go through. We will talk a little bit about the mathematical formulation, because it has some nice properties, again, compared to something like decision trees. Right? If you think about this, there was basically no math in the lecture about decision trees. There was one equation for entropy, which was kind of trivial. And then if you tried to do the quizzes, then you would encounter a different equation for Gini index, which measures pretty much the same thing slightly differently. But the whole idea behind decision trees was very intuitive one. It wasn't really mathematical. Right? The SVMs give you a different perspective, because here the very intuitive problem of making decisions is actually phrased in a very concrete, kind of hardcore math problem. And then you solve the math problem, and then you kind of try to see how this math problem relates to the intuitive problem which you started with. And in a sense, the lecture, as was given, is maybe a little bit too much on the mathematical side. And you can quite clearly see that the professor giving this lecture, he is very much a kind of from math background. He enjoys those kinds of mathematical analyses. And I think it's yes.
Do you think that this mathematical knowledge, is that mostly for people wanting to do really deep research, or is there some? I mean, I do know some math, but I think that it doesn't really help me a lot when I try to do some machine learning in general, when I'm just using it. Mm-hmm. So do you think it's only useful when you try to do more deep research, or what do you think?
No, I think it actually is useful when you are using those tools as well, because if you understand the tools better, you will be able to use them better. And there is always a way of doing machine learning, which is get some data, try 20 different methods with 5,000 parameter settings each, and you will get some kind of results. But this is not the best way of doing data mining, machine learning. much better way is to actually understand the problem, see how it relates to the tools that you are using, and be able to, in some kind of principled way, figure out a good tool for this particular task. It's not always obvious, but I think having at least some level of understanding is definitely useful, even if you are not going to be creating new methods.
Okay, yeah. There was one thing I was thinking about with the SVMs. In many of, maybe I just didn't see it in the lectures, but in many of the examples, they showed perfectly separable data sets. So I was wondering how it performs when you can separate all the points with a perfect with some line.
Mm-hmm. So this is what he talks about in the second lecture. So you still
have
something to wait for. But yes, basically that's kind of the way this was organized. The first lecture was about the basic case. Given that we have data which is separable, in the last couple of minutes he actually talked about the nonlinear transformation as well. But even then, the data was supposed to be separable. They assumed kind of no noise. But that was the well, more optimistic version of it. So in the second lecture, he talked about what to do if you have some noisy points and how this changes. So if we compare,
I mean,
go ahead.
Yes, he said that this. I think the name was kernel function could of course be defined in different way, and he talked about some kind of catalog where you can find already defined kernel functions, and then if you need to define your own that you can't find in the catalog, you had to do some mathematical research to investigate if that was valid or not. And I heard him, but I must admit I did not really understand how to do that kind of investigation. Is that something you think is needed for us to apply this, or could we just come a very long way just by applying kernel function from the catalog?
I think you don't need to worry about defining your own kernel functions. I think it's very unlikely that you will ever encounter a case where you would need a specialized kernel. And if you are in such a situation, then you will need to find somebody who understands this anyway. So
yeah,
there is so many kernels available that it's very unlikely that you will encounter this problem.
Where can we find this catalog of investigated kernels?
Interesting question. I guess if you Google kernel function list, if you Google for a list of kernel functions, there will be some mix-up with like Linux kernel and so on. But like at least a couple of links here will have a number of those.
Maybe you can send that link out after the lecture today.
Yeah, sure. I can do that.
Yeah. Does it say there in that table also some kind of advice for what kind of situations a kernel is good to use, or is it just trial and error, or how to use that catalog?
That's less clear. I think so. The one that I have found here doesn't tell you what different kernels are good for. They just describe the kernels.
Yeah, but for me that's new to machine learning. How to start?
This is tricky. I think that this will mostly come with experience. It's difficult to give some kind of rules of thumb. Basically, as usual, the starting point would be to start with the simplest kernels and go towards more complicated ones. That's probably a way of looking at it.
Yeah, when you say complicated, that's a mathematical definition of the kernel. Then it can be less. or more complicated, of course.
Mm-hmm. Yeah, you can think of it also in terms of computational complexity. So the more complicated kernel will take longer time to compute. But in general, this is related to, I mean, it's also related to what we talked about before, the complexity of the hypothesis space. That the more complicated hypothesis you allow, the more likely you are to overfit. You can think about the complexity of the kernels kind of like the size of the decision tree to some degree. Limit yourself to small decision trees, you will not overfit so much. If you limit yourself to simpler kernels, you will not overfit so much. So one example is linear kernel or polynomial kernels of different degrees. The higher the degree, the more complicated it is.
Yeah, so you can look at it as a feature space. I mean, the more complicated a kernel you have, the more features you have, which could allow you to create, for example, a linear decision boundary. So, so the question kind of can boil down to, I mean, do you know what features are good for solving your particular classification problem? I mean, the kernel is supposed to help that to generate those features that are useful for separating the two classes.
So if we try to compare SVMs with decision trees, as we said, that they are trying to solve pretty much the same problem. What do you think are the strong and weak points of something like SVM versus decision tree?
I'd say that the decision trees have an easy time to deal with the factor variables because it can just create features yes and no on them, and I guess the SVM would have a little harder time.
I'm not sure I understand what kind of variables you mean.
Like binary variables, yes or no, or something like that.
Yeah, well, yes or no, that's just 0 or 1, right? So I'm not sure if this is
maybe it's the same
for SVMs. You're welcome. So no, I think both of those can handle different kinds of attributes. If you have something like categorical attributes where you don't really have ordering of values, like red, green, yellow, those would be slightly easier for decision trees than for SVMs because it's difficult to put them in space, right, in metric space. And for decision tree, you can have you can just split on all the possible values. So
yeah.
But there are techniques for dealing with that, so it's not really a big difference. Any other ideas? Which one is computationally easier? Which one is able to handle bigger data sets?
As I understood, it's SVMs, because there was a lot of simplifications in the math there. Is that correct?
There was a lot of simplifications in the math. They solved the problem, or they phrased the problem in a way which is reasonably easy to solve. On the other hand, the idea behind SVMs is to solve the optimization problem in an exact fashion. And so we actually are trying to find an optimal solution. The algorithm for learning decision trees, that's a greedy algorithm. So it's not trying to find the optimal tree. It's just making decisions, whatever looks best at a particular stage.
But when you say it like this, then I don't understand what we said before, because I had the idea. Of course, it was wrong, but that it was more automatic in some way in the SVMs. But isn't it that then that you get an optimal solution in the SVMs, and that is mathematical built in the method, and that's not in the decision trees? Or
yes,
maybe I'm wrong.
The solution you are getting from decision tree learning algorithm is not optimal. But both methods are fully automatic in a sense that
I see. Okay.
You get a data set, and then you give the data set to a computer, and it will calculate the actual model. So there is no, of course, when you present it on a whiteboard, then you do it in steps. But the actual method in practice, in both cases, it's fully automatic. There is no thing that the user needs to make.
But is it so that you can handle more complex problems with the SVMs, since you move to this infinite dimensional space and back? Or
so, but it kind of depends on what you mean by can you handle more complex problems. Definitely, it handles different kinds of problems. Because one way of looking at it is, if you think of a data set with, I don't know, 1 million examples. I mean, lecture said that 10,000 is easy, 100,000 might be a problem, million might be too hard to solve. I guess it's probably somewhat outdated now. I guess the lecture is probably from, let's see if I see, it might be 5 or 6 years old. So I guess by now the progress might have been so that we can handle an extra order of magnitude. But if we go to something like 10 million examples or so, it probably would still be a problem. Because you are actually trying to solve this quadratic equation or optimization problem, and you are trying to solve it in an optimal way, taking all the examples into account. And if you think of how the decision tree was operating, you would iterate over all the attributes, and then you just need to calculate this quite simple metric like the entropy for this single attribute across all the examples, of course. But if you have a millions examples, it's basically just summing up 1 or 0 over all of those examples. That's an easy operation. Right? There is nothing particularly complex there. Of course, you need to do it several times, because you need to do it over all the attributes, and then you need to do it for every level in your tree. But this only consists of quite simple operations. So you can actually learn decision trees from quite a bit bigger data sets than what SVM is capable of handling. On the other hand, one of the problems with decision trees is that they are actually quite susceptible to overfitting because of this kind of greedy fashion. You will start in the root of your tree with the attribute that seems to be best overall, but it doesn't really have to be the best one. And if you make a bad decision at the top, then the rest of your tree will also, they will kind of propagate this error to make it harder to create the rest of the tree. So especially for complex problems, the decision trees are more likely to overfit, while the SVM, because of this kind of optimal way of solving the optimization problem, is more likely to find the the decision boundary which has fatter margin, so that it lies farther away from all the points, which means it is less likely to overfit.
Mm. But can you explain? In the last lecture, he said a lot about this. I think it was called this penalty term or factor, this C. And he discussed that, and you can set that value to avoid overfitting. But how to compare that to the problem of avoid overfitting in decision trees? Because in SVMs there were actually a method, as I understood that.
Yes, so in decision trees there are also some methods. We haven't really talked about this, but there are different methods to avoid overfitting in decision trees, and the most common one is pruning of decision trees, which is basically saying that you build a decision tree and then you cut the lowest levels based on things like how many examples you have had to train that and so on. This is one example of something similar to the C parameter. For
could you repeat that about pruning? I did not get that fully, please.
So the main reason why decision trees would overfit is that as you are going lower and lower in the levels, you have less examples from which you are learning, right? Because if you have your data with, let's say, 3 attributes, and you make a split on one of those, you end up with 2 subtrees. Each of those subtrees will only have a subset of examples. It doesn't have to be exactly half, it would probably be somewhat close to half. And that means that on the second level of the tree, you will have 1 more split. So then in each of the nodes, you will end up with a quarter of examples. So every subsequent node you are creating is based on smaller number of examples, which means it's more likely that it's actually not a correct node, but it's based on the kind of noise in the data or just some kind of random factors, not the underlying true function. So one way of avoiding overfitting it in decision trees is to make sure that you don't create additional nodes when you don't have enough examples to really make good decisions about what those nodes should be or how those nodes should look like. And that's called pruning. So you create the full tree, and then you remove the nodes at the bottom, which are basically not really trustworthy. And in a sense, that this fills a very similar role as the C parameter. So for those who didn't watch the second video, how much did you watch? Nothing at all? Not good. So we are down to 2 out of 4. So basically, the second lecture is, among other things, about soft margin classifier. So the idea is that you allow some number of points to be within the margin. So basically, you consider them noise. You penalize the optimization problem for their occurrence, but you don't really require a decision boundary which correctly classifies all the points. And if you think about it, this is similar to what would happen with a decision tree, because if you have a decision tree and you create some kind of node which is almost pure except for one example, so let's say it's all from class A, but there is just one example from class B, what you can do is you can keep splitting, keep adding extra nodes to the decision tree until you have a perfect separation, but it's most likely not really worth it. If you only have one example, it's much more reasonable to assume that one example is noise, rather than try to figure out what attribute is a good way of splitting it from the rest of the node. So this is exactly what the C parameter tries to achieve, and you could achieve similar things in decision trees with, for example, this pruning event. But if we take maybe one, yes, go ahead.
Yeah, why have you chosen SVMs and decision trees? Are they the most common or the most easy to understand, or because I think there are even more methods? Or
oh yes, there is a lot of different methods. But if you look at what methods are actually successful, I think the three most common ones is decision trees, SVMs, and neural networks. So I will also talk about neural networks a little bit today.
Yeah.
I think, well, today, I think the neural networks beat everything else in terms of popularity, just on the basis of deep learning. I mean, this is the biggest current hype. But if you look at the lecture there, this lecture is from, at least partially, from before the hype about neural networks or the learning. So the big hype in machine learning before deep learning was actually about SVMs. The one before was about ensemble learning, so things like random forest. A lot of this was centered about decision trees. So I actually wanted you to see the things that at various times in the past have been considered the holy grails of machine learning. And in a sense, as you can see, they are becoming more and more complicated because SVMs is significantly more complicated than decision trees. Neural networks, and especially deep learning, is even more complicated than that. So those solutions are not getting any easier. But the main reason for starting with decision trees was just how intuitive they are. The concept of decision trees is just very natural for people. It captures how we are thinking about. The reason for SVMs is that I wanted to show this nice computational properties or this nice mathematical formulation to show that you can actually phrase the machine learning task as a clear-cut, very precisely defined mathematical problem. You can solve it, and you can use this solution to classify new data. And then later today, I will talk about artificial neural networks, which basically you cannot really ignore today. You have to talk about it at least a little bit. But the artificial neural network are in a sense an exact opposite of SVMs in terms of they have an extremely complicated mathematical formulation. And from the theoretical point of view, we actually don't really understand very well how they work. They are very much the result of a large number of people trying large number of things, and at some point kind of stumbling upon a solution that happens to work, but we don't really know why. I think those things make it for interesting discussions.
But do you mean that even you as mathematicians don't know all the details of the neural networks?
Well, I wouldn't say that we are really mathematicians. So no, we don't know all the details. But there is actually nobody who really knows all the details.
But how come this method came up from the beginning? Because normally, or the most common case is that some mathematician do some statement and investigate something, and then it inherits from there. But this was different then.
I think you have a very optimistic way of thinking about science. The accidents play a much bigger role in science than your statement would suggest. But I mean, in a sense, so there is, of course, at least some level of theory behind the neural networks. It's not like we have absolutely no idea how they work. I think one of the big things about neural networks is just how easy it is to make small modifications to them. If you think about decision trees, if you would try to come up with a similar but different way of creating decision trees, it's not that easy. And you might come up with 2 or 3 different ways, but you couldn't really come up with 1,000 different ways. The similar thing with SVMs. Their whole point is based on such elegant mathematical foundations that there is not that much wiggle room in coming up with different solutions. And I mean, if you look at those question and answer sessions, they ask about different distance measures and so on. There are some things that you can play with. You can try different kernels, but the actually amount of flexibility in this general method is not that high. And that's a very extreme contrast to something like artificial neural networks, because in artificial neural networks, you have pretty much an infinite way of, or infinite number of different types of networks that you can try to come up with. You can play with architectures and different functions within neurons and so on. And that's one of the reasons why it has gotten so successful, because people have started taking this general idea and modifying it in different ways. And because there is so many people doing machine learning, so many different settings for so many different problems, that this kind of, I would call it at least semi-random exploration has actually worked, because people stumbled upon ideas that work through continuous improvement. You take some solution which worked well for somebody else, turns out there is 1,000 different research groups that are trying to improve on it. Even if we don't really understand how it works, some of those research groups will come up with something that actually helps. And then based on this, that there will be some kind of progress.
Is there any applications today where you actually use decision trees and SVMs?
Yes, there is a lot of those.
So in what kind of problems or practical implementation do you use a decision tree? When do you use an SVM, and when do you use an ANN, or artificial neural network?
So there is one part of this answer which is easy. There is actually not that many applications where artificial neural network deep learning has been successful. Despite all of this hype, the problem with deep learning is that it requires a lot of data. And here we are not talking about thousands or tens of thousands of examples. Here we need at least millions, if not billions of examples before we can actually do some kind of learning. So there is a lot of settings in which artificial neural networks are not really that good. There is a number of ways of cheating this, at least a little bit, because artificial neural networks are very good at transfer learning. So they are very good at taking a solution to one problem and applying it to a problem which is different but somewhat related. So the big success stories for artificial neural networks is basically image processing and to some degree natural language processing and speech processing. But they are basically very good at pretty much all kinds of image processing, because you can train them on huge image sets, or you can pre-train them on huge available image sets, that the public ones from internet and so on. And then you can just adapt them to your particular problem using a lot less data. So basically, if you want to be using especially deep learning, that there are two ways of doing it. One is you either need to have somewhere between millions and billions of examples, or you need to be able to find a pre-trained network which solves a problem which is somewhat similar to the problem you are trying to solve. If those things are not fulfilled, then you would probably use either SVMs or decision trees. And what you would probably do is not like a single decision tree. You would probably do maybe random forest or some other kind of ensemble. But to figure out if what you want to be using is actually decision tree or SVM, that's a trickier question. There are no really good kind of rules of thumb about which of those methods will work better. I guess the biggest, now it's really hard in the abstract to say when decision tree will outperform SVM and when SVM will outperform decision tree.
Yes, understood. But so artificial neural network is more for classifying vision and speech. But what kind of data do you think is typical for decision trees and SVMs? Is more like you mentioned what's called fault analysis from data from vehicles, or what kind of problems are we talking about that you use for where you use SVMs and decision trees?
So mostly what you would use this if you have some kind of let's say interesting features already available. So basically you do a lot of machine learning of this kind based on some kind of, or pretty much any kind of databases. You can do classification, for example, of different customer types based on their purchases. You can figure out what kind of marketing campaign will work for different people based on their socioeconomic profiles. You can be doing predictions of, or maybe a regression problem of how many plane tickets you will sell at different prices. You can do classification.
It's like Cambridge Analytica with Facebook.
Yes.
Okay, yeah, I get it.
Actually, Facebook is one of those cases where you might end up with enough data to use deep learning, so that there is some work on using deep learning for that. But a lot of analysis in social networks is done using random forests or SVMs.
Yeah. So the key difference is the amount of data used for training, basically.
Yes, pretty much. So if you think about how the machine learning field has been changing kind of over the years, the initial approaches were based on the idea of you have very little data and you really need to extract as kind of, you need to squeeze every single bit of information out of this data. And this is kind of what the SVMs were designed for. Right? The idea here is that you have your data which represents your reality, and your goal is to find this optimum line which separates your classes. And you are willing to go to quite big lengths to make sure that your line is really the best possible line that you can have. So in that context, you can think of SVM as a kind of clear evolution from decision trees, decision trees were basically based on the idea of, let's try to think about how people make decisions. People make decisions by looking at if-then rules in a kind of hierarchical way, which is what led to the development of decision trees. But then turns out that we still have a lot of problems like this. That not everywhere we actually have big data, right? Especially when we start talking about data which has actually been processed and understood, because it's very easy to collect a lot of data, but if you collect a lot of data without really putting the effort to figure out what this data should represent, then you are collecting a lot of noise and only a little bit of actually useful data. So we don't really have necessarily good ways of quantifying it, but if you intuitively think about what's the ratio between the useful data and useless data, in general, the more data you collect, the less amount of useful data will be in it. Right? If you spend the time to actually design your database correctly, to actually collect your data in a careful manner, then you will be collecting a lot less data, because this data collection is orders of magnitude more expensive, but you will actually be able to trust this data much more. So there is a trade-off there in between how much you really want to, how much work you want to put up front before you start collecting data in order to make sure that the important things that you are interested in actually end up in this data, versus how much you want to put later on in processing the data, which was easy and cheap to collect, but which was probably collected without too much thought, and which might contain some interesting insight, but might also end up being almost pure noise. So in that context,
I read about, sorry, continue please.
So in that context, there is a big difference between approaches like SVMs and decision trees, which are designed for data in which you assume that most of the data is actually meaningful. Right? There is some amount of noise, but you assume that the actual useful information outweighs the noise, versus those kind of more modern like deep learning techniques, which are focusing a lot on processing data in which most of the data is noise, and you just need to find the actual information. And images are a good example of something like this. Right? If you consider image represented as I don't know, 1,000 by 1,000 pixels, most of this data is noise. There is very little actual information in this. So the approaches that you should be using in order to get something useful out of it are necessarily quite different.
Yes, I understand. Good explanation. Thank you.
I recently read about an application where they used, and I think you said too, Slavomir, about an application where they do predictive maintenance of some kind of machine. I think it was an electric engine, and then they measured the vibration and could detect when some bearing maybe was on the way to break. What kind of algorithm do you think was used in that case? Could we estimate or guess something?
Well, so that's probably not really enough information to make a guess. I guess so. If I was to make a guess, I would say that the core of the algorithm was probably expert knowledge, because there are several different ways of doing it. Right? If you have vibration sensors, then what you are actually collecting is time series data of the vibrations. And if you want to directly analyze this data, it's going to be quite difficult. Just because this is an example of this data which has a lot of noise and very little useful information. If you would collect enough of this data to try something like deep learning, then it would probably be quite successful. But what you would need is probably data from millions of hours on thousands of machines before you could really get good results. So in many cases like this, what really happens is that there is some expert knowledge that goes into extracting useful features out of those the raw signal. So, for example, there are obvious cases, like instead of just measuring the vibrations, you would do some kind of Fourier transform, or you would do some wavelength analysis, or any other way in which you take the expert knowledge about how you expect a bad bearing or something like this to manifest in this data, and you extract features which capture this kind of information. And then, as a second step, because it's difficult to really do it fully manually, right? To make sure that you are very precise in extracting those features. But if you find good features, you find rules or equations to roughly extract them from the data, then you can use machine learning on top of that to actually kind of learn the parameters, the thresholds, and how to combine different features into good decision. And then it could be pretty much any kind of algorithm, but I would assume that something like SVM would work quite well.
Thank you.
So maybe just to kind of slowly finish this discussion part, because I do want to talk a little bit about neural networks still. But if we talk a little bit about this concept of support vectors, because this is quite important in understanding the whole point of SVMs. So what are the support vectors and why they are so important as to even give the name to the whole method?
You mean why the support vectors are important, or?
Well, let's start with what they are. So what is a support vector?
But I understood that the basis for the support vector machines is that you define a minimum tolerance for dividing the different classes, and that the support vector machines were the length of those were actually from the points nearest to the border, and defined from the point nearest to the border to this plane that divides these data points.
Mm-hmm. Yes, so the basic idea is that support vectors are the data points which lie closest to the boundary. And so those are the ones that actually define the boundary. So in a sense, so if those are the points that are closest to the boundary, they define the boundary, does it mean that other points are useless? If you would remove all the other points and just leave support vectors, would the learning result in the same?
I want to say yes, that it only depends on all the support vectors.
Everybody agrees?
I didn't quite hear the question because there was some noise in the background.
So the question was, if you only keep support vectors, if you remove all the other data points from the training set, will you get the same learning result or not? And yes, basically that's the. If you look at some or think about some of the examples that was shown during the lecture, right? Very clearly the points that are those insight points, they don't really contribute much, or they don't contribute anything to the actual decision. Because if they would disappear, the line would still be exactly the same, the line that separates the two data sets. Now, this only holds for the hard margin case. Of course, in the soft margin, when you actually allow for noise, that's not necessarily the case, right? Then those internal points can still matter, because without them, you could consider the support vectors as noise. But that's a slightly different issue. So one of the important features of support vector machines is that they actually are able of finding those points which are the most important ones for learning. Because if you go back to something like decision trees, for decision trees, we don't really have such a concept as vectors. The decision tree is affected by all the points, also the ones which are far away from the decision boundary. And that's actually not necessarily a very good thing, right? Because it's not that useful for those points which are not close to the other class to actually influence the decisions. But because the decision tree looks at the data attribute by attribute, it doesn't really look at it in this kind of aggregated way. The approaches are quite different. And then, so one last thing that I wanted to talk about is why did the whole idea start from this concept of linear separability? What's the main point behind this? Because then if we have data which is not linearly separable, and a lot of data usually isn't linearly separable, then we have to be doing this either the kernel trick, or we have to do those nonlinear transformations. Why couldn't we just start by a nonlinear separation between data? Any ideas?
Maybe to make sure that it also works on linear separable data.
Well, but if you have data which is linearly separable, you can always separate with other shapes as well, right? So let's say we could limit ourselves to polynomial separation. So we could say that we want to have data which is separable by a polynomial of degree up to 10. And then linear would be a special case of something like this. So that there are two main reasons for starting with something like simple like linear separability. And there is one which is kind of practical / computational complexity. If we are going to find an optimum for minimum for this optimization problem, the simpler the optimization problem, the more likely we are to be able to do it for large data sets. Right? So in case of linear separability, we end up with quadratic programming problem, which is somewhat easy to solve. We can do it for 1,000, 10,000, maybe million examples. If we would be looking for a more complicated decision boundary, the corresponding optimization problem would become even more complicated. And then we wouldn't be able to efficiently solve this. So that's one side of the coin. The other side of the coin is also that, as we have talked before, when you want to be doing machine learning, in order to get good generalization, you want to start with the simplest possible hypothesis. Okay? So the more complicated hypothesis space you use, the more different hypotheses you have in your hypothesis space, the more likely you are to overfit. So what you actually want to do is you want to find the simplest possible hypothesis. So in this particular case, the idea was that, well, linear separation is pretty much the simplest hypothesis we can imagine. So instead of trying to keep the original data and try to build more and more complicated hypothesis space, which will allow us to separate this, the SVMs have decided to do it the opposite way, to keep the hypothesis always simple. So you never get a hypothesis which is more complicated than a linear hypothesis, and instead do transformations of the data. And because they have this concept of support vectors, which means that they don't really consider all of the data points, they only consider a hopefully small subset of the data points, the data transformation is less harmful than the hypothesis transformation. Because if you do even very complicated data transformation, you can still end up with a small number of support vectors, in which case you know that your transformation hasn't been very harmful in a sense. Doing this kind of evaluation on a more complicated hypothesis would be a lot harder. Okay, so I think that's pretty much what I wanted to talk about concerning SVMs. Any final questions or discussion points? Because if not, I will move to artificial neural networks.
You
Yes.
said that.
Please, yes, please do so. I have to go at 16:30. So.
Okay.
You said that first we had decision trees, then SVMs, and then neural networks. What do you foresee in 5 to 10 years to be the dominant method?
I'm not going to make this guess. That never ends. Well.
Okay.
Those kinds of guesses.
It's hard to say. I mean, that tells me that it's very hard to say then.
Yes, definitely. No, all of those guesses, when people make, they sound just ridiculous after a time. Like, I mean, there is a world market for maybe 5 computers, and
yeah,
we are terrible at predicting those things. So I'm not even going to try.
Okay.
So to talk about artificial neural networks, basically the kind of core concept here is that we like to think that our brains are quite smart, so let's try to emulate those things. So basically, can we copy the structure and the way our brains operate and train them to do the kind of problems that we want to do? And there are some challenges. For example, we don't really understand how brain works. We have some ideas. The core concept of artificial neural networks was actually created in the 50s. And back then, we understood even less about how our brain works. So this is a very simplistic model. Our brains are actually quite big. The human brain has roughly 10 to the power of 11 neurons. Elephant has twice as many because they have bigger brains, obviously. Our neural networks are nowhere on this level. Our neural networks are much smaller, even the deep learning ones. But we are still trying. So the core concept is to try to do something similar to what a brain does. And if you think about the very simple way of looking at what we understand about our brain consists of neurons. And a neuron is this kind of strange thing which is connected to some other neurons, and then it can be either active or not. So if you are trying to mathematically formulate this, you would end up with, let's say, a circle like this, which has some inputs, x1, x2, x3. Those would be connections to other neurons or connections to input or output or senses, actuators. There are different weights on those connections. And then the neuron itself will operate according to a particular nonlinear function. Turns out, if you only have linear functions in neurons, you cannot do much, because then the whole thing becomes just a simple linear system. But if you put nonlinear function, you can start getting some interesting results. So basically, the output of a neuron is just a function of weighted sum of its inputs. Conceptually, quite simple. So if we talk about the simple perceptron, let's try to use it for solving exactly the same problem as always before. We have binary classification problem. We want to classify something as A or B, red or green, +1 or -1 for simplicity. So in this case, what we can use is we can use sine function as our activation function. So we will have sine over vector of weights times vector of inputs. This can be any kind of any size. And that means that we will get +1 or -1 depending on whether this sum inside will be bigger or smaller than 0. And so this is just a way of going from a continuous set of inputs into +1, -1. So we have a clear decision for our classification. Doesn't have to be binary decision, of course. We can do any other function here, but for simplicity, I will talk about binary ones. Turns out that the actual sine function is not that good if you use something like Heaviside or whatever, because it's not differentiable. So it's always 0 or always -1, and then it jumps suddenly. Sudden jumps are not great. So a much more common function to actually use in practice is something like the logistic function. There are some other examples as well. But the basic idea is that we want to avoid the jumps, and if we use a function which is roughly 0 for values which are smaller than 0, and roughly 1 for values bigger, with something in the middle which is not very big, then it works just as well for the classification problem, and makes it much easier to actually do calculations on. But the basic idea behind the perceptron learning, if we again go back to like the 60s and so on, is that we have some desired output. So we have a number of examples. As before, it could be our visiting the restaurant thing, or it could be any of the examples that was shown based on SVM. So what we know is that for every example, we want to have either +1 or -1, depending if this example belongs to class A or belongs to class B. And if we want to train our perceptron to actually recognize this, we can start with random settings. So we have random weights. We pick one of the examples from our training set, and if the classification of this example is correct, so if our neuron gives the same answer as we expect, then we don't need to do anything. If the classification is wrong, then what we do is we basically update the weights of this neuron so that it's more likely to give correct answer on this example in the future. And then if we can guarantee that doing this will eventually converge into something which gives correct decisions for all the examples, we are great, because then we will keep doing this until we make no more errors, and then we have learned some kind of a function. So if you look at the equation here, you take the old weight and then you modify it basically based on the learning rate times the expected output times the corresponding input for this weight. And the basic idea is that if you have made a mistake in your classification and your example should get +1, but instead it got -1, what you want to do is you want to lower the weights to make it more likely that this example will give you -1 as an answer later on. So this is why you use this Fn in the equation, which basically means that if you want the final result to be lower, you need to lower the weights. If you want the final result to be bigger, you need to increase the weights. And then you also multiply this by the input value for this particular weight. And the idea here is that because the final result from your neuron depends on all the inputs, however, it depends on those inputs to a different degree. But it also depends on the weights to a different degree. So in here, for example, if the final result of the y value is too big, you want to lower all of the weights, but you also would like to know which of those weights contributed the most to the result. And if you think of it, the one that contributed the most was the one associated with the highest value of the input. In particular, if one of the inputs was 0, then you don't want to modify this weight because you don't know if this weight is too high or too low. So this is why you use the XIN in here. You want to distribute the credit for this mistake according to how important each of the weights was. And here again, we are back to more approximation. So basically, the idea behind perceptual learning is that this is a heuristic which is guaranteed to eventually converge to a solution which will never make any mistakes. But there is no guarantee that this will be the best solution for any particular quality criteria. So SVM is actually the only of the popular algorithms which has those strong mathematical foundations with a guarantee on actually finding the optimum solution. All the other algorithms are approximations. So if we look at an example of how this could actually work, right? So we have our neuron. Let's say we have two inputs. We have x1 and x2, two-dimensional input. We want to learn the end function. Right? So you have f. End function obviously is +1 if both inputs are true, and -1 in the opposite cases. We can start with the initial values of w, our initial weights being -half, 1, and 1. We could pick them at random or whatever. And we have our learning rate 0.3. So this is enough for us to start thinking about, or to start actually learning this perceptron. So if we think about it, all the knowledge that the perceptron has is actually encoded in the weights. So the weights that we have is the kind of current state of the perceptron. So what that means is that for those particular weights, the red line is the decision boundary for this perceptron, right? Everything on the left-hand side will be classified as -1. Everything on the right-hand side of this line will be classified as +1. So what we can do is we can go through our training examples one by one and start looking at how does the perceptron do. So clearly what we want to do is we want to have this line move towards upper right. Let's see if the perceptron can actually figure it out. So if we start with the first example here, this one is correctly classified. There is nothing we can do, or nothing we have to do. Now we move to the next one, and now we notice that this one is actually not correctly classified, right? So now we have to do something. We have to modify the weights of the perceptron in order to make it more likely to be correctly classified. So if you remember the rule here, how we modify the weights, it's old value of the weights plus learning rate times expected value times the input. So here is what happens, right? We have W0 equal W0 minus ni times 1. So it becomes minus 0.8. W1 becomes W1 minus ni times 0 plus 1. Right? So as you can see here, we have 3 different weights. We have 2 inputs. The first weight is so-called bias. So this is using kind of a fake input, which is always 1. I will not go into too many details. But then this particular example has x1 equal 0 and x2 equal 1. So this is where this 0 comes into the picture and this 1 comes into the picture. So we look at all 3 weights, we modify them according to our equation, and we end up with new weights. So now, after learning from this one example, our neuron has weights minus 0.8, 1, and 0.7. Luckily enough, in this case, it already classifies this example correctly. There is no guarantee that after a single update, the example will be classified correctly. It might be that we need to present it multiple times. But here, I didn't want to make this example too long. So after a single iteration, we are able to correctly classify this example. Right? And as you can see, it makes sense. We had neuron with this kind of decision boundary. We have found an example which was misclassified. So we are changing this decision boundary, kind of moving it closer to the misclassified example, like this. And then we go to the next example. So here is third example. This one is correctly classified. There is nothing we need to do. And then we go to the last example. Again, incorrectly classified, so we need to do an update. Okay, so again, for every weight, we take the current value of the weight, we multiply it by the corresponding input learning rate, and we get new weights. So after this step, our neuron will look like this: minus 1.1, 0.7, 0.7. So this is the red line, which is now the decision boundary for this neuron. So everything to the left of this line will be classified as minus 1. Everything on the right will be classified as plus 1. And as you can see, this now correctly classifies all of our examples, so we don't need to be doing any more training. So that's a very, very simple way of learning. You take a very simple unit like a perceptron, you do a very simple update based on one example at a time. And the idea is that after a number of such steps, you will end up with the correct function. There are some nice things about perceptron, but there are also some problems. So actually, using this kind of learning, assuming your learning rate is low enough, you are guaranteed to find a solution in finite time if a solution exists. So if you have data which can be classified by a perceptron, you will actually find the correct solution. The problem is this kind of learning is too simplistic to really generalize to more complicated networks. If you just look at a single single example at a time, and you only modify the weights based on whether this classification was correct or not, it really doesn't work when you have bigger networks. And the problem is you need to have bigger networks because a single perceptron can only learn linearly separable data. So we are again back to this very, very simple case. And that's quite clear. You can see that the decision boundary for a single perceptron like this is just a line. If your data is not linearly separable, a perceptron will not be able to actually learn it. The main reason why we are talking about perceptron and why those kinds of approaches actually work is that we are not talking about the single perceptrons doing classification. We are talking about networks of perceptrons. So here, again, we had an example of the input of our neuron was the original training data, and the output of this neuron was the decision that we wanted to make. But when we think of how the brain is organized, most neurons are connected to other neurons, not to muscles or sensors or eyes or things like that. So the actual artificial neural networks are organized in terms of layers of such perceptrons or many perceptrons connected to each other. And the problem with such a network is that you need to have more complicated way of learning it. So in this particular case, for learning in perceptron networks, we are using gradient descent. So the basic idea is, of course, to figure out what kind of error a network is making, find or assume that this network, the function captured by this network is differentiable. Then we can calculate gradient of this function. So then we can basically figure out how should we modify the weights so that the error decreases the fastest. Right? So I don't think I need to introduce the basic idea of gradient descent, but the basic concept is, of course, to kind of always go downhill. If we have a measure of the error that the network is making, and the simple case is we can measure the error of the network just as a difference between the expected output and the output our network produces. So if we know this error, what we can do is we can calculate the gradient according, we can calculate the gradient, or how does the error change if we change different weights in the network, and we just go towards the fastest dropping error. And the whole idea here is that this actually allows us to combine several single layer perceptrons into a network which together can learn functions which are a lot more complicated than just linear functions. So artificial neural network basically consists of a large number of interconnected perceptrons where each of them is making a linear decision, but together they all contribute to much more complicated decisions. And there are several important aspects in order to build those kinds of networks. One was, as we said, if we want to train them using gradient descent, it's important that we can actually differentiate the total output of the network so that we know which weights we should be changing in order to reach the low error as soon as possible. The other part of it is that we want to be doing this learning in an iterative way by showing the network one example at a time and adapting the weights to this particular example. Just as we have shown it for the single perceptron, we can do exactly the same thing for the multi-layer perceptron. So if we take what used to be the most common example until maybe 10 years ago or so, was the artificial neural network with a single hidden layer. So just as you can see here in the picture, you would have some number of input neurons, where basically you would connect your input training data to those neurons. You would have a single hidden layer, and then you would have output layer, which captures the decision that you try to make. So for example, for a binary decision, the output layer would consist of two neurons, one that would correspond to class A, the other one would correspond to class B. If you look at such a simple, conceptually simple network structure, of course, you can have different numbers of neurons. So this is just a conceptual way of looking at it. You still need to decide how many neurons in different layers you want to have. But you can quite easily calculate the actual output of every neuron in this network for different activation functions. And then one can prove that you can approximate any kind of continuous function with a sufficiently large artificial neural network with a single hidden layer. So that's one of the reasons why people have focused on one-layer networks for quite a bit of time. There is a mathematical proof that it's enough to approximate any kind of function. So why would you go into something more complicated? Training such networks was reasonably easy because it was easy to calculate the gradient. It was easy to kind of figure out what was the contribution of different neurons to the solution and so on. And if you want to do something like this, you can see, again, I will not go into the math here, but what you want to be doing is you want to be able to compute the gradient of the error for different changes in the weights. Right? This is just basic math. We want to figure out how does the output of the network changes given our input. If we choose the activation functions in a smart way, smart meaning something that will be easy to differentiate, we can quite easily calculate what is the what is the contribution of a single weight to the final result, so that we know how much we should be changing those weights. Right? You can calculate what's the actual output of the network. Here is the equation again for single hidden layer. We can differentiate that. We know what will be the effect of changing the weights. We can figure out for a particular learning rate that we want, how much should we be changing those weights in order to reach the minimum as fast as possible. Again, in an approximate way. Gradient descent is also a greedy algorithm. So this is the kind of core idea behind artificial neural networks. We build a network of kind of collaborating neurons. Each neuron is very simple, but together they can approximate more complicated functions. We know how to change the weights in individual neurons in order to modify the final output. So this is, again, just a simple visualization of a gradient descent. And depending on your point, you want to move in different directions the ways that will lead to fastest decrease of the error. And obviously, there is no guarantee that you will reach the global minimum using something like this. But the whole optimization problem here is way too complicated to actually find the optimal solution. So we need to focus on approximations. There are other ways of doing this, going beyond.
May I ask a short question?
Yeah, sure.
Can you go back to page 22?
22. Mm-hmm.
You presented the mathematics behind this. Does this mathematics assume that the nodes in one layer, in the figure here, we can see that one node in the layer to the left, every node is connected to a layer in the next layer? Does the mathematics assume that this is the case, or is it different configuration? Let's say that it's not always connected to all the nodes in the next layer, or
Yeah. So this equation here assumes fully connected network.
yeah.
That's not the only way of doing it, right? There are networks not fully connected. I mean, you can always. The fully connected case is the most general one because you can always say that there is a connection, but the weight of this connection is 0, kind of like there wouldn't be a connection. In which case you can always have exactly the same equations if you want. But especially when you go to more complicated structures, you actually don't want to have a fully connected network. You want to have networks where either the weights, or either not all the neurons are connected, or not all the weights are different. So you could, for example, you have different ways of duplicating the weights across layers and so on. So then the equations would change, right? So the equation is doesn't always look the same way.
And the neurons, the number of neurons in each layer can also vary. So it's not always the same for all the layers either. Or?
Yes, definitely.
Is that the main thing that differs from different networks, the number of nodes and how they are connected, or are there other things that differs from the different algorithms?
So number of neurons is not really that crucial. It's more about the connections, because the problem with a network, even network like this, is that you have a lot of connections, right? Which means the number of connections corresponds to the number of weights that you have in your network, and the number of weights corresponds to the complexity of the hypothesis. Basically, just as the more nodes you had in your decision tree, the more complicated the decision tree was, and the more likely you were to overfit. We have exactly the same problem with neural network. The more weights you have in your neural network, the more complex your hypothesis, because every change in a weight means a change in the hypothesis. So the more weights you have, the more likely you are to overfit. So a lot of what deep learning was about finding good structures for the network where you can actually have more neurons without adding more weights. That's a kind of short explanation.
Yeah, thank you.
Yeah. So again, when the original idea behind training neural network was this simple gradient descent, there are more clever ways of doing it. One example is resilient propagation, where you actually modify the learning rate depending on how your training is going. Because one of the biggest problems with gradient descent algorithms is that figuring out a good learning rate is tricky, because if you pick your learning rate too slow, you will never really reach good solution, because you will be changing things too slowly. If you pick your learning rate too big, you are likely to jump over good solutions, and you will basically end up doing some kind of random search instead of guided search. So resilient propagation is one way of actually updating the learning rate based on the results you are getting. So the idea here is that if, as you are doing your propagation, or as you are doing your gradient descent, if you keep going in the same direction, then you want to increase the learning rate. You basically, if you are always going in the same direction, you want to go faster. But if you change direction, if that means that, well, something has happened in between my previous iteration and this one, which means that I've actually jumped over something interesting. And that means that you should decrease your learning rate so that you focus more on this interesting area. Again, this is a little bit more mathematical. It's just an example of how you can play with the idea of finding the minimum. But the goal in both cases is exactly the same. Right? You want to find the set of weights in the network which minimizes the error that the network makes. And here is also one interesting example of how you can think about the overfitting problem, because neural networks are different from both decision trees and SVMs because they are examples of online learning. So you basically learn one example at a time. And you can reuse your examples, but still you present an example to a network, you get an update of the rule of the weights, you now have a different model, you present another example, get an update, you get yet another model, and so on. So basically, in neural network, this is called training epochs, but that means that you keep getting better and better models pretty much continuously. If you look at SVMs, there is just a single optimization problem. You present all the data to SVM, and you get an answer. That there is no iterative process. If you look at decision trees, there is a little bit of iteration, but not that much, because basically at every step you create one node in your network, or one node in your decision tree. But there is not that many of those steps, and it doesn't really make that much sense to kind of track the accuracy at different levels, because at every step you look at all the data anyway. The neural network training is quite a bit different, because you present examples one after another, which actually means that you can be tracking pretty much continuously how does the classification error look like. And then you can see what is shown here on this plot, that as you train more and more, the training error, the red line, will continuously decrease. So the error you are making on a training data set will get smaller and smaller. But at some point, the validation error, so the error that you are getting on the test set, will start increasing. And this is very clear visualization of the overfitting problem. At the beginning, once your network doesn't know all that much, it just learns. It learns the kind of true properties of the data, gets better with every learning step. But at some point, it actually stops learning the true interesting knowledge, and it just starts to learn the specifics of this particular training set. It starts to adapt to the error, to the noise in the data, and so on. And that's the moment where you want to stop your training and say, there is no point in training anymore because it will actually do more harm than good. So in many cases, you actually want to do something like this in order to decide when the network has learned enough. You want to set out a validation set in order to continuously estimate the test error in order to know when to stop training. I mean, it's possible to say that you will train for a given amount of time or given number of training epochs, or until the gradient change becomes too small. But what you really want to be doing is you want to be finding this sweet spot of when the validation error is actually the lowest. And then one more thing which is related to that, which I actually haven't talked about before, is if you want to know at what point the validation error is actually the lowest, what you need to do is you need to find a way of comparing models. And this is a little bit tricky because what we are working with here is pretty much probabilistic or random variables. So if you have two models, let's say model A and model B, you don't really, you kind of never really know the actual expected classification error that those models will make. What you can do is you can test this model many times, and you will get some kind of random results which depend on the actual true classification error. And so this will be realizations of random variable, because depending on what kind of data you present to your model, you might get better or worse results kind of at random. So what you will actually end up with is some kind of distribution of classification errors based on cross-validation or any other way in which you are actually measuring this. And then what you can do is you can do, for example, this kind of error bar plot, where you say the average accuracy of model A is, let's say, 80%. The average accuracy of model B is maybe 50%, but there is some kind of confidence interval or error bar on top of that, based on how widespread the different numbers have been. And this is in particular important when you are doing artificial neural networks, because of how many different parameters you have when you decide on the neural network, right? Even if we assume that we want to pick the simple case with one hidden layer network, there is still a number of parameters that we need to determine. We need to figure out how many nodes in this hidden network. We need to figure out which input data to use. We need to figure out what kind of preprocessing is better, and so on. So what we can do is we can create a lot of different models based on the same principles of artificial neural networks. And then what we want to do is we want to know which of those models is actually the best. And one way of doing it is to do cross-validation, compare those different models, and then do a plot like this, where we show there is some difference between the two models, but then we can start asking question of, is it statistically significant? So can we really trust that this difference is inherent in those models, or is it just random? But by chance, one of the models happens to be luckier than the other and gives us slightly better results. So those concepts are obviously not specific to artificial neural networks, but again, they are more important here because you can easily create so many different neural network models. So now, if I go briefly in the direction of deep learning, I mean, deep learning as a concept is quite, or probably too complicated to cover in a course like this. So we will not go into actual details, but we will just give an overview of why is it so important. So the core concept behind deep learning is that they do what can be called representation learning. So instead of requiring experts to come up with good features, they can create hierarchical features in an automatic way. And after the SVM lecture, you should know why representations are so important, because the kernel does nothing more but just change the representation. But here is yet another example. If we have data as on the left plot, we have some blue points and some green points in this kind of coordinate space. It's difficult to learn a good classifier. Right? It's not necessarily very obvious how to separate those. If we try to learn decision tree, it will probably make quite a bit of error on this data. But if we transform this data into polar coordinates, we will end up with the data on the right-hand side plot. And if we try to create decision tree now, it becomes trivial. This will be just a single node which perfectly separates this data. And so again, this is something that you could do with SVMs and kernel, but this is also something that kind of underlies the most important parts of deep learning. So the core idea behind deep learning is this kind of repeated composition. So you would start with some kind of data. And here I will use images because it's one of the most successful areas for deep learning. So you start with the input data in terms of pixels. And as we have talked about, pixels have actually very, very little information, right? Any single pixel doesn't really tell you much about the image. There is a lot of noise in the pictures, in the actual values of pixels, and so on. So this input layer actually has a lot of noise and not that much useful information. So what deep learning will do is, at different layers going kind of upwards here, it will start building up features which are useful for actually doing the task. So in this case, object identification. So maybe in the first layer, it will start detecting edges. Right? So you could see different kind of edges that it detects. Then, based on those edges, in the next layer, it will start detecting things like corners or contours of objects, and so on. In the next layer, based on those, it will start detecting parts of objects. So it could detect a face, or it could detect a wheel of a car, and so on. And then finally, after some number of layers, it will be able to identify, let's say, car, person, or animal. And the point here is that here what the network is actually building is building hierarchical representations. So those edges, that the same feature called, let's say, edge, is useful for detecting many different contours and corners. So it's kind of reusing the knowledge about edges at different places of the image. That's kind of the core idea behind it. And until deep learning came into the picture, we didn't really have a good way of building those kind of hierarchical features. So a lot of this work was done by people, by experts, by researchers. So we had a number of different ways of extracting features from images that came as a result of kind of years of research. And then it turned out that you can do those kinds of things automatically in an actually better way. Again, the problem with those kinds of approaches is you need a lot of data for doing this. Yes?
Are the features that you talk about here, are they something that the human eye can percept? So can you actually get something visually if you look at the different layers in this kind of image recognition algorithm?
Yes, in some cases you can, not always. There are some, so there is two aspects to it. One is the network actually learning features which make sense to us? And the answer to this is yes and no. So some of the features that the networks extract are meaningful, and some of the features we haven't really been able to understand. So it learns some things which don't seem useful for us. And we actually, again, don't know if this is good or bad. So if we should learn something from the network, meaning those features actually are useful, or if we should improve our network so to not learn those features because they are not useful. We don't know that yet. The other side is also how do we know what the network has learned? So there is a lot of research in visualizing those middle layers in the networks. So we have some ways of doing it, but again, we are not yet perfect at it. There is still different information that the network has learned, which we don't have a good way of visualizing. So if we think about what deep neural network is, we've talked about simple networks like a single neuron and do logistic regression. If we have one hidden layer, we can start talking about, okay, now we can learn any kind of function. Deep neural networks is just about, let's add more layers. And the main question is, of course, why would we? Because we want to do those hierarchical features. And as we've said, you can learn any kind of function with just single hidden layer. The problem is you cannot do it with a small network. So again, there are mathematical proofs that you can have a small deep neural network which learns a particular function, and we know that it's possible to learn the same function with much shallower network, but that shallow network would need exponentially more hidden units. So basically you are saving a lot by having this kind of deep neural network structure. The problem here is that the network structure needs to be well adapted to the structure of the function. So here is an example with XOR functions, where you need a particular network structure to learn it efficiently. But the challenge is, if we don't know the function that we are trying to learn, and if we knew it, we wouldn't be learning it, how do we come up with good network structures which can learn a lot of useful functions? So that's where most of the research in deep learning actually is. Coming up with new network architectures, which we expect or empirically prove are good for different types of functions that we find interesting. And just to kind of show you a little bit about what the kind of hype that we are having with deep learning today. So this is the number of people registered for NIPS conference. This is one of the main deep learning conferences. So between 2002 and 2016, there was some increase in the number of people registered. But things have changed quite a bit in 2017. Right? I mean that this line, I don't know if you can see my mouse cursor, but this line looks nothing like the lines before. So something significant has changed. That's obviously not only about deep learning, because if you look at the so here is an example from Stanford, people who are registered for their AI course. 150 students 2015, 350 16, 750 in 2017. So basically, every year the number of students doubles. So apparently in 24 years, everybody on Earth will be enrolled in this Stanford course. We have some time left, but not very much. But of course, the main reason why this kind of hype happened is that those kinds of networks actually work. And interestingly enough, they work on the type of challenge which is very easy to understand because they work on images. And until recently, people have been very proud of our ability to understand images. There was basically no way computers were even approaching human levels of competence in understanding images. But this has changed. That's actually the biggest change that neural networks have brought into the picture, deep learning has brought into the picture. On simple tasks like recognizing objects and images and so on, actually deep neural networks now outperform humans. They are better than humans. And most of this work is focused, as I said, on building good architectures. So the kind of starting point of this was convolutional neural networks. So this is a type of a network which has a very strict architecture, looking at where the connections are not to all the neurons in the previous layer, but only to a very small region in the previous layer. So for every region in one layer, you will have a single neuron in the next layer, which kind of combines the information from this region. And the idea itself is not necessarily new. I mean, it goes back to 70s, 80s. What has happened is basically two things. We've gotten a lot more efficient computers. Actually, there are three things, because we've gotten more efficient computers. We have gotten a lot more data. The kind of performance that we can get today wouldn't be possible even 5 years ago, mainly because we didn't have that much data. And also there have been some changes in the actual learning and architectures. So that today's architectures are not exactly the same as the ones from 79. They have the same, they are based on the same concepts, but the actual architectures are different. So the basic idea is the convolutional neural network, and then there have been a number of modifications to it. So one popular was AlexNet in 2012, quite based on similar concept, but a different architecture. The core reason for why deep learning actually works is regularization. So if you think of it, you have something like 1.2 million examples. But in the network of AlexNet size, you have between 5 and 100 million parameters. So if you go back to the lecture about SVMs, the idea there was that you can bound the expected error by number of parameters divided by number of training examples. If you look at it here, you have 100 times as many parameters as examples, which means that your error you would only make error. That will be only over training. So the main idea behind deep learning is to actually build this kind of architecture, but then limit the number of active parameters as much as possible. And I will not go into details, but there is a lot of work on doing that. I will skip the slide about adversarial. I just want to show some pretty pictures. Here is an example of how you can visualize the kind of things that the network learns, right? So here you can see in some level of abstraction what kind of features the network is actually learning for different kind of concepts. So that was for convolutional neural network. Here is for a different kind of network called VDG. So that's what I wanted to talk about today. Any final questions, comments?
Yeah, I have one about the data transformation, because we've touched on it a couple of times, and I was thinking if it can be used as a part of maybe a feature creation step to actually get data into some format where it fits better to the algorithm you're going to use. If that is maybe a way to get more accuracy or something.
Yes, that's definitely a way of getting more accuracy. So if you can come up with better features, you can improve things a lot. And of course, the ultimate end of it is you just want to have one feature which will tell you to which class your example should belong, right? And then learning becomes really, really easy. The tricky part is, of course, finding the right balance between how much work you as an expert want to put into this versus how much work machine learning algorithms can handle. That balance is not easy.
Is there like a bunch of common transformations that can be used, or is it more of is it a question of looking at data and then thinking about like more of an intuition thing?
So it depends how unique your data is. So if there is a whole bunch of typical features, and it can go from anything like Fourier transform. This is a way of transforming data that's popular. It can be, for example, if you look with vibration data, as was mentioned, that there is a whole bunch of papers about here are good features to extract from vibration data. If you look at images, there is a whole bunch of features. If you look at speech, there is a whole bunch of features. If you talk about, so basically the idea is if you can find some other examples of other people who have used data which is similar to yours, you can figure out, or you can see what kind of features they have used. In general, that's harder. If you say, well, I have data which is different than what anybody has ever used, then you probably need to come up with your own features.
Okay, yeah, makes sense.
Okay, great. Thank you very much for today then.
Yeah, thank you.
Bye-bye.
Bye.
Bye.